All right, Chemistry 3111. Let's get started with Chapter 16, which deals with conjugated pi systems and pericyclic reactions. I'm not going to explain pericyclic reactions yet, but I do want to review the word conjugated with you because it's come up several times in Organic Chemistry 1 and maybe a little bit this semester. Conjugated means you've got, some kind of carbon chain and you've got double bond, single bond, double bond, single bond, right? So if you have double and single bonds alternating, that's considered to be a conjugated system. And if you're wondering, well, does that mean that benzene, for example, would that be a conjugated system because you have double, single, right? Absolutely. That would fall under the umbrella of conjugated as well. And if you're wondering, why are conjugated systems a thing that we have to discuss, I can explain that to you really quickly. Okay, so if I put this compound, let's not worry about benzene yet. Let's just delete this. It's not even that pertinent to this chapter. If I put a box around this compound, could anybody tell me what's the hybridization of every single carbon atom in this molecule, in this fully conjugated compound? That's right, Audrey. Everything in here is sp2, right? Tiana, Maria, you're all 100% correct. So that means, oh, son of a gun, I didn't mean to do that. That means that every single atom, every carbon atom, has a p orbital on it, doesn't it? They all have a p orbital. This is my artist rendition, which isn't super pretty, but you get the idea. If they all have an unhybridized p orbital, that means that you have orbital overlap across the entire thing. Okay, I shouldn't use the word thing in chemistry class, but you get what I'm getting at here. There's complete orbital overlap the whole way across, okay? And that's going to be important in this chapter. So let's move forward and let's take a look at the different classes of dienes. So I just went over what a conjugated diene is, and that is going to be the major focus of this chapter. It's going to be conjugated dienes where you have double, single, okay? Pi bonds are separated by a single bond, that's conjugated. Accumulated diene is where the pi bonds are adjacent. And if you're wondering, what's this dot here? The dot is a carbon atom. So this is a shorthand we use. Sometimes people just put a space in between it like this, okay? And then you assume there's a carbon atom there, but it's more correct to put a dot. So when you have two pi bonds on the same carbon atom, we put a dot there. That's something that I don't know if I've ever shown you before. So accumulated, yeah, you have two pi bonds, but the thing is that all of the p orbitals, right, since this carbon is sp hybridized, it's got two unhybridized p orbitals. Those two p orbitals have to be perpendicular to each other, if you remember. And so therefore, we don't have complete orbital overlap in a conjugated diene. Anyhow, and then isolated is nothing more when they're separated by more than a single bond. So you've seen Avogadro's number of examples of isolated dienes, all throughout the course. So there's nothing really new there. All right, so if we look at the orbital overlap of these unhybridized p orbitals in the accumulated, conjugated, and isolated dienes, it will help clear up what I was just trying to explain to you. So when you have accumulated diene, right, you have a pi bond and a carbon that's got another pi bond on it, you see that you have one set of p orbitals, right, that makes a pi bond, but then you have another set that's perpendicular to it. I'm going to try to circle this as best I can, right? They meet each other at a 90-degree angle, and so you don't have a complete orbital overlap, right? There's no orbital overlap between this orbital here or this lobe here, right? They're 90 degrees apart from each other, and so that's why it's not a major focus of this chapter. We're mostly going to look at conjugated dienes. So this would be showing the orbital overlap of 1,3-butadiene, right? If you have 1, 2, 3, 1,3-butadiene is what you would call this molecule. But again, every carbon in here has an unhybridized p orbital, and you can get complete orbital overlap across the entire thing. And then when you have something that's isolated, like this guy here, you get a double bond here, then you've got two single bonds. Well, those pi bonds aren't connected to each other in any way, shape, or form. And again, the reason we have the conjugated ones highlighted here, or kind of in bold, it's because that is what we're going to focus on most of the time. Now, you might be looking at the conjugated diene that I drew here, which is the same one that was on the previous slide, I think, okay? And you might be wondering, well, could I change one of those double bonds? Like, could I change this double bond for a that's not very pretty, for a carbonyl? Could this be an oxygen? Well, that's a pretty crappy artist rendition, but yes, absolutely you can, okay? So you can have a conjugated ketone. We call this an enone. Get it, right? You've got an enone from an alkene and an one from a ketone, hence the name enone. But yes, if you look at the hybridization of this carbon, this carbon, this carbon, and this oxygen, everything is sp3 hybridized. So yeah, you have a fully conjugated system there. If you look at this ring at the bottom, yeah, you can have a heteroatom like a nitrogen involved in a conjugated system. If we think about the hybridization of this nitrogen, it's got 3 regions of electron density. Therefore, it's sp2 hybridized. So what does that mean? It's got an unhybridized p orbital on it, doesn't it? Yeah, absolutely, right? It's in this pi bond, okay? And that's overlapping with, there's one here, so on and so forth. I won't draw them all in, but that's completely a thing, okay? So we have conjugated systems here that could involve a carbonyl or could involve a heteroatom. There's nothing wrong with any of that. So let's start out with a little icebreaker here in way of questions, and I'm going to get you guys to solve these ones for me. It says, for each of the following compounds, identify whether each carbon-carbon pi system is cumulated, conjugated, or isolated. So what I'm going to do is this. I'm going to circle this part of cis-aconitic acid, which you might have seen in the Krebs cycle before. Right, you've heard of the enzyme aconitase, maybe. Anyhow, this part in red, how would you describe that? Would you describe it as cumulated, conjugated, or isolated? Anybody? Yeah, thanks. That would be conjugated, absolutely. So conjugated, there we go. All right. So we got that one. What about this one in blue? If I put this guy up in blue here, how would you describe this one? Yep, thanks, Maria. Absolutely, that's isolated. Perfect. What about this next compound here? Osamine or osamine? I'm not even sure how to pronounce that compound. Found in essential oils. I heard a stand-up comedian say, when did the word snake become replaced with essential? Anyhow, I thought it was really, really funny. Maybe you guys don't share my sense of humor, but anyhow, I thought that was a good one. Anyhow, how would you describe these bonds here? Anybody? Yeah, that would be conjugated. Jeepers. And this one over here, this one would be isolated, right? So we'll put that over here, isolated. And the last one, okay, we have a couple of pi bonds here. How would you describe these ones? Yep, exactly. Conjugated, yep. And then you have one that's isolated over here by its lonely self. There we go. So let's see here, isolated. All right, there we go. Students usually nail that. All right, well, let's take a look at how would you make a diene, right? Let's say you wanted to make a compound, you know, like this, like 1,3-butadiene. How would you make that? You know, how would you make this compound, right? There's got to be a way to do it. And there's a couple of things you could do. It says here, a sterically hindered base can be used to form dienes via an elimination, right? So if you took tert butoxide and you took this alkyl or this compound and you treat it with tert butoxide. So if I draw my butoxide on, right, you have what you'd call that an alpha proton here. So let's see, this is going to get abstracted. You form the double bond, you lose the bromine, done. And similarly, if you had this dibromide, you would just do 2 E2 reactions, right? You would do one on, you do one on this side, and then you do the same thing over here, right? The same thing twice. It would be a double E2, and you get the same thing, right? So this is just good old-fashioned E2 chemistry, so nothing really new here. So that's how you would make a diene. And what's interesting about the bond, the sigma bond or the single bond between the two sp2 hybridized carbons in the middle of 1,3-butadiene, if you look at their bond length, you see the bond length, it's actually a little bit shorter than a regular sigma bond, right? Right. This is a sigma or a single bond, right? Same thing. And it's a little bit shorter than this sigma bond. And there's a couple of reasons, there's a couple of ways you can explain that. The simplest way is just to look at the hybridizations of the carbons, right? If I look at this carbon and this carbon, they're both sp3, as you see shown down here. And if I look at this carbon and this carbon, they're both sp2, as we have shown down here. Well, which orbital is smaller, an sp3 or an sp2? Anybody? Which orbital is smaller? Yeah, it's an sp2 orbital. It's smaller, right? Thanks, Audrey. And if the orbital is smaller, that means that when you overlap to form a sigma bond between the two sp2 hybrid orbitals, the bond is going to be shorter, right? Because the nuclei have to get closer together. So there you go. It's nothing more than that. That's the answer. And that's one of the answers. There is a second answer that is covered in MO theory, which we only touch on, but that's the reason why the bond is shorter. And check this out. It says heats of hydrogenation show that conjugated dienes are more stable. I don't know why I have a question mark by that, but anyhow, it shows that. So remember hydrogenation. Hydrogenation is when you take an alkene, right, and you treat it with hydrogen and nickel or palladium or platinum. That's what hydrogenation is. So if you were to take two molecules of one butene and hydrogenate them, it's going to release 254 kilojoules of energy. But if you take 2 moles of 1,3-butadiene, you think about it, you're doing the same thing. You're hydrogenating 2 moles of double bonds. Shouldn't it release the same amount of heat? Well, you see that it actually releases less heat. It releases 15 kilojoules less heat. And so that tells you that there's a stabilization of 15 kilojoules per mole when you have bonds that are conjugated. So there's some inherent stability that comes with something being conjugated. And this isn't really completely related. Well, it is in a way related to aromaticity. You know, when I talked about benzene with you, I don't know if I told you this in Organic 1, but I'll just kind of throw this in as an aside, and we'll look at this in the coming days. If you take a compound like this, I told you this is an aromatic compound. Well, there are lots of aromatic compounds that we're going to learn, but aromatic doesn't necessarily mean fragrant. It means stable is what it means. So you can try to draw the connection there. Well, with that in mind, let's see if we can rank these compounds in order of increasing stability. So I'll write over here most stable, and I'll put down here least stable, like that. So which one of these is going to be the most stable compound? Anybody answer that one? Heck yeah, it's D, right? Because D is the only one that has a completely conjugated system in it. Yeah, so D is going to be the king of the castle. Which one's going to be the least stable? Yeah, absolutely. A is going to be the least stable because you've got two isolated, right? This isn't conjugated and this isn't conjugated. Where it gets interesting is if we look at B, B has a conjugated diene in it. Maybe I should use different color here. B has a conjugated diene. So let's see, it's got something conjugated, right? And then it's got something isolated. But in this one, we also have, in C, we also have something that's conjugated, and then we also have something that's isolated. So how are you going to decide? Well, it's going to be based on substitution. If you remember in chapter 8, the more substitution you had on an alkene, the more stable it was. And so if we compare B and C, if you look at the diene or the conjugated portion in B, you see that's connected to a carbon here. Well, maybe use my red pen, right? That's connected to a carbon here, 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 right? So it's got all these different carbon here as well. It's got all these carbons attached to the carbons of the double bond and only one hydrogen on it. Whereas this one, it's attached to a carbon here and here and here, but it's got 1, 2, 3 hydrogens on it. So B is more substituted, and so B is going to be more stable, and C is going to be down here, and then A is going to be the least stable of all. So again, if you don't remember that concept, that's found in chapter 8. So chapter 8, the more substituted an alkene is, the more stable it is. All right, perfect. Thanks, everybody. Thanks, George, Jaylyn, Tiana, great. Awesome. Let's move on from there and talk a little bit more about this whole concept of a conjugated diene, right? And if you think about this molecule, so let me just help you out with this, since I'm going to use this word a lot, right? This compound is called, 1,3-butadiene. However, there's a free rotation around a sigma bond, isn't there? And so we can have 1,3-butadiene where you have a dihedral angle of 0 degrees between the two methylenes here, or you can have a dihedral angle of 180 degrees between the two methylenes. And we call those the S-cis and S-trans conformations, okay, of butadiene. So this one that I drew up here, this would be the S-trans, okay, S-trans 1,3-butadiene. Now, if you're wondering what is S-cis and S-trans, I remember cis and trans, right? I taught you cis, right? And I've taught you trans way back in the day when we studied alkenes. So the S in S-cis and S-trans stands for sigma, right? Because you have free rotation around a sigma bond. But both of these conformations have some stability to them because in both of these conformations, namely the S-cis and the S-trans, we can have complete overlap of all the p orbitals, right? You have complete and perfect overlap in both cases, okay? In the S-cis and the S-trans. Now think about it. If you rotate this 180 degrees, it takes you to the S-trans. But if you were to rotate this only 90 degrees, you're not going to get the S-trans. It's going to be, right? You're going to end up breaking the interaction here, right? There's going to be no bond or no overlapping, I should say, in between those two orbitals, those two p orbitals, and those two central carbons, okay? So if we take a look here, in order to break that orbital overlap, it costs you 15 kilojoules per mole of energy. And I didn't ask you on the last slide, I should have asked you, but I was going to ask you, which one do you think is more stable? And I'm sure you all would have guessed the S-trans, right? S-trans is more stable than the S-cis by 12 kilojoules per mole. Why? It's just because of steric hindrance, right? In this one, the two methylenes are blocking each other. Again, they have a dihedral angle of 0, whereas in here, there's no steric hindrance involved, all right? And the S-trans versus the S-cis. So here's a picture of what happens when you get to the it's not an activated complex, but until you get to the highest point here of this potential energy, right? Because you break the planarity, if you will, or you break the overlap when you go from the S-cis to the S-trans, right? So there's no overlap between this p orbital and this p orbital, so you don't have a continuous orbital overlap, and so we consider that to be unconjugated. It's not conjugated. All right, so that covers the first two sections of chapter 16. There you go, we're done. Now I'm going to move on to section 16.3. The thing about molecular orbital theory is I'm only going to ask you some basic questions about this on your quiz and the homework. So I'm going to go over the things that you need to know about this section, which is not really the entire thing. Now, if you go back to the idea of MO theory, this would have been covered by your instructor in General Chemistry 1. So at UCCS, that's Chemistry 1401. And if you don't remember, I can tell you when you would have seen this. If you remember studying things like H2 and HE2 and Li2 and B2, and does anybody remember doing this at all? And N2 and O2 and all that stuff, right? And then you had a sigma, and then you had a sigma, then you had a sigma star, right? And then you'd connect them together, over 1s orbitals and all that kind of stuff. If you remember that even like a hair, that was molecular orbital theory as it was covered in general chemistry. Now, there are some sections of chapter 16 where you have to use MO theory to solve some synthesis problems. However, we don't cover those sections. So again, what I'm going to cover with you over the next few minutes is just the basics of what you need to know in Chemistry 3111. So I'm going to erase all this stuff because I don't want to scare anybody who goes to my YouTube channel and says, what's this dilithium? What do I need to know that for? Okay, so it says, our little review of molecular orbital theory. It says, if you have two atomic orbitals, they overlap to form two new molecular orbitals. So what you can take away from that is the number of atomic orbitals, okay, the overlap is going to be exactly equal to the number of molecular orbitals that are formed. So if I have a molecule that's got 4 atomic orbitals, it's going to have 4 molecular orbitals. If it's got 6 atomic orbitals, it's going to have 6 molecular orbitals. So that's number 1. And the thing is that atomic orbitals were associated with, well, you guessed it, just an atom, right? You took an orbital that was on an atom, and then you overlapped it with an orbital on another atom, and you made a bond. The thing about molecular orbitals is that they're orbitals, but they go across an entire molecule. So they're associated with an entire molecule. And let me just stop right here. If you're going, oh man, what is he going on about? Man, like how many different ways do we have to represent the molecule? First, you taught me S and P and D and F. Then you mixed them together to make sp2 and sp3 and sp. And we drew orbital overlaps and all this stuff. And now you're giving me orbitals that cover the entire molecule. So how am I supposed to draw an orbital that covers, a giant molecule like cholesterol? Well, first of all, I would never ask you to do that. But remember that what we're using here, these are models that were developed by human beings, okay? And we can't shrink ourselves down to the size of an atom or a molecule. So we come up with models to help us explain the behavior of atoms and molecules. And we adjust our models depending on the situation. Sometimes atomic orbitals are not sufficient in order for us to understand or to explain the reactivity of a molecule. So that's why we cover MO theory. So let's go look at the last point. It says the overlap of the p orbitals in ethylene result in a bonding molecular orbital and an antibonding molecular orbital. So all we're looking at here is the molecular orbitals that result from the overlap of the two p orbitals on each of the carbons in ethylene. So this is just an ethylene molecule, okay? And both of the carbons in ethylene are sp2 hybridized. So they both have an unhybridized p orbital. And now on the picture here, you see that they shaded the lobes, they shaded them like this and then like this, okay? And they said, okay, well, when those overlap, there's two possibilities. They can overlap in phase, right, and form a bond, or they can overlap out of phase. And technically, that's not overlapping. They can be out of phase. And in that case, they don't overlap. And we call them a bonding molecular orbital and an antibonding molecular orbital, respectively. Now, hopefully you remember that in every atomic orbital could hold two electrons. Well, the good news is that all the molecular orbitals can handle 2 electrons. So if you take 1 electron from each 2p, then both of them are going to go into the bonding molecular orbital. And what you need to know is that a bonding molecular orbital is going to be more stable than an antibonding molecular orbital. All right, so the number of atomic orbitals is equal to the number of molecular orbitals. Molecular orbitals extend over the entire molecule. We can use them to explain the reactivity of molecules when atomic orbitals don't cut it. And a bonding molecular orbital is going to be more stable than an antibonding molecular orbital. Well, the thing about ethylene, this molecule here that's shown on this page, right? This is ethylene, okay? There's only 2 carbon atoms here, and so there's only 2 molecular orbitals. But if we look at a more complicated molecule, okay, like 1,3-butadiene, okay, so here's 1,3-butadiene. We have 4 p orbitals that overlap to form the conjugated system. So this is 4 atomic orbitals. And what did we say? We said the number of atomic orbitals is equal to the number of molecular orbitals. So how many molecular orbitals do we get? We get 1, 2, 3, 4. There you go. Now what's different here, or what I'm going to introduce here, I guess, is that if you go to the lowest energy molecular orbital, it's going to have no nodes. That means every p orbital is going to overlap completely. They're all going to be in phase. And we go from 0 to 1 to 2 to 3, so on and so forth, nodes. You see the same thing back here. If you look at this bonding molecular orbital, there's no nodes. What is a node? It's where there's a breakage, where you have p orbitals that aren't overlapping. And here we have 1 node. So we go from 0 to 1. We go back to this example here with 1,3-butadiene. We have 4 molecular orbitals. We start with 0, 1, 2, 3, and so on and so forth, but we can only go up to 3, of course, in this case. We have that many nodes. Now, if you're going, now, what's the difference between this here, that's drawn in 3 dimensions, versus this? Well, if I was to ask you to draw, or if you were asked as a chemistry major to draw this on a quiz, would you be able to do it? Draw it in a beautiful 3D model? No. And so we like to use this shorthand way of drawing molecular orbitals to help us, represent, molecular orbitals with ease. And so we go from 0 to 1 to 2 to 3 nodes. And what you notice is that since each p orbital has 1 electron and each molecular orbital can hold 2, we have a total of 4 electrons. So where are they all going to go? They're going to go in the first 2 molecular orbitals, right? They're going to go in the one with 0 nodes and 1 node. Now, something that is not really going to be all that pertinent to us are what we call the homo and the LUMO. So I'm not going to go into a huge amount of detail about this, but if you decide to read all of the textbook, the last orbital or the highest energy orbital that has electrons in it, we call it the HOMO, which stands for highest occupied molecular orbital, right? Because there's electrons in here. And then if you look at the unoccupied molecular orbitals, which would be this one here, we call this one the LUMO, which means lowest unoccupied molecular orbital. And if you're wondering, well, if I don't need to know it, why are you telling me it? Well, it's just an FYI, I guess an FYI concept. And there's a lot of interesting chemistry that occurs between the HOMO and the LUMO. In fact, we will look at some chemistry that involves these two molecular orbitals, but we won't get into the details of it. All right, so there we go. I've already explained what nodes are, so I'm not going to go into much more detail about that. And then this molecule is 135 hexatriene, so that'd be 1, 2, 3, 4, 5, 6. So 1, 3, 5 hexatriene. I mean, there's nothing really that I want to show you on here, except if you have 6 atomic orbitals, you get 6 molecular orbitals, 6 electrons. They all go into the occupied or the 3 lowest energy molecular orbitals. This one here would be the HOMO, right? This one here would be the LUMO, is what you'd call that. Anyhow, I won't go into any more detail about that. I don't think I will. Anyhow, so if you're wondering about this whole HOMO and LUMO thing, we call those orbitals frontier orbitals. That's what they're called, okay? These ones here, these are the frontier orbitals. And again, you can see there's an electron getting excited into the LUMO, and then that becomes the new HOMO. Anyhow, again, I'm not going to cover any of this with you. Like I told you before we got started, I tried to teach this one semester, and then I realized that it wasn't part of the ACS, so I learned the hard way that I don't need to go over this. But if you want to read it on your own time, you can. And just as an interesting thing, where I went to graduate school, we call this frontier molecular orbital theory when you study frontier molecular orbitals. My supervisor at graduate school was super into FMO theory. It was his favorite thing to talk about. And so even though it was something I didn't know a whole lot about when I started my graduate studies, I came out and sure thought I did, because it's, you know, it was his favorite topic of conversation was talking about FMO theory. Anyhow, I digress. Let's get into section 16.4. So we're going to switch gears and get into something that's a little bit different. I'm not going to talk about molecular orbitals anymore, really. And we're just going to take a look at an electrophilic addition. You're like, hey, I see the word Markovnikov on here. I like that. Good. Everybody in this room, or everybody who's hearing the sound of my voice, should be able to draw this mechanism, right? This is a good old reaction from chapter, I guess this would be chapter 7, really. Just a Markovnikov addition of HBr across a double bond. The rich get richer. You form a stable carbocation. It undergoes nucleophilic attack. Nothing new there, okay? So this is just review, what I have on the top. Where it gets a little bit more interesting is, check this out. See where I have the little green sidebar here? Check this out. If you have 1,3 butadiene, and you treat this with HBr, I mean, what the heck's going to happen? Well, you get a mixture of jeepers, okay? You get 2 products, okay? If you count the carbons going backwards, like this 1, 2, and I just mean backwards the way it's written, and if you number them like this, okay, and 1, 2, 3, 4, since the hydrogen from the HBr, it got added to carbon 1, okay, in both cases. We call this one the 1, here's my black pen. We call this molecule the 1,2 adduct because the atoms were added to carbons 1 and 2. And this one we call it the 1,4 adduct because the 2 atoms were added to carbons 1 and 4 respectively. All right. And I bet you that just by looking at this for a few seconds, you could probably come up with an idea of how you would make, or where both of these compounds come from, right? So here's the answer. You do your same old Markovnikov addition, right? The rich get richer. So if I have these 2 blue protons here, right? I still have those 2 blue protons here. I add the proton from the HBr. You see they only have 1 proton over here, right? There's still just 1 proton here. And so now we get a carbocation, but it's what kind of carbon? Ooh, it's an allylic carbocation. And therefore, it's going to have a resonance form. And does that resonance form exist? Of course, it's a hybrid, right? And so you can think of the carbocation as being on this carbon, what I called carbon number 2 on the previous slide, or on carbon number 4, as I called it on the previous slide. So now I know what you're all thinking, and you're 100% correct. If you're thinking, well, does that mean the bromide could just attack here, or the bromide could attack here? And those are pretty crappy mechanisms that I just drew. But if that's what you're thinking, you're 100% correct. That's exactly what happens. And if you're going, well, there's no way I could do anti-Markovnikov because then I'd form a primary carbocation. It's not resonance stabilized. You'd be 100% correct on that too. So usually students have this thing figured out pretty quick because they'll say, okay, well, if I add to the carbocation on carbon 2, right, if I number this 1, 2, 3, 4, I get the 1, 2 adduct. And if I add it to carbon 4, 1, 2, 3, 4, I get the 1, 4 adduct. All right. So give me a thumbs up if you follow me on the mechanism just by looking at it for the first time. If you just look at it and say, hey, that makes some sense, even if you're with me 60% of the way, that's good enough because you're going to have to practice these because we do a few different, we do some asymmetrical ones, which are a little more complicated. So with that in mind, with all that cool stuff in mind, let's take a look at this situation here. Besides HBr, if you try the same kind of thing with bromine on a conjugated diene like this, you still get a 1, 2, and a 1, 4 adduct. The mechanism is exactly like you think it would be, right? You get a carbocation, and then that's allylic, and of course it has 2 resonance forms, so you can get nucleophilic attack from either carbon. Okay, now if you understood this, this part here, or you're just saying, oh, I'm just seeing this kind of for the first time. I read the book twice before I came here today, but anyhow, it's still kind of new to me. Now we're going to kind of turn up the heat a little bit, and we're going to look at a couple of problems, excuse me, where we have some situations where we're starting with a diene, but it's not symmetrical. Okay, if you look at this diene here, you'll notice I've taught this class for a long time, and students will sometimes look at this and say it's symmetrical. It's not a symmetrical diene. It would be symmetrical if you had a methyl group here. Then it would be symmetrical. But notice there's no methyl group there, so this diene is not symmetrical whatsoever. All right, so what's going to happen in that case? Well, there's 2 possibilities for Markovnikov addition, isn't there? There's 2 different ways that the rich could get richer here. And so what we need to do is we need to take a look at both of those possibilities. All right. Sorry, I misspoke. So what we need to do is we need to make an allylic carbocation, and then we need to take a look at both of the possibilities of making an allylic carbocation. That is what I meant to say. All right, so with that in mind, let's take a looky here. So again, what we want to do is make an allylic carbocation. Let me just write that down because I kind of misspoke there. So allylic carbocation. So we're not going to follow Markovnikov's rules here necessarily. We want to make an allyl or an allylic carbocation like this, right? We want to make something that's resonance stabilized. Man, how did this? There's so many thumbs up. Who did that? Did somebody click the thumbs up button and like put a cup of coffee on it or something? That was crazy. Oh, space. I like it. All right, cool. I've been teaching remotely for several years now. I've never seen that before, so that was a new one. Good to know. All right, that was amazing. Okay, so are you with me on that? Sorry, I misspoke when I said Markovnikov. I saw the word Markovnikov and got carried away. What we're trying to make are allylic carbocations. Okay, so we're gonna need this whole page just to solve this one problem, and then I'll go to a blank space to solve the second one. So let's get into it here. Let's see, I'll erase this giant circle that I have here. So I'm going to redraw the HCl molecule like so. And what are we going to do? If we want to form a carbocation here, right at this position, what would we need to do? We would need to add the proton here. So let's do that. So if we added the proton to that carbon, Then we end up with a carbocation here. Go. And now we have an allylic carbocation that looks like this. Could you draw the resonance form of this allylic carbocation? I hope so. All you have to do is move the pi bond over here, and then you're going to end up with something that looks like this. So now we're going to have the pi bond over here. We've got our positive charge down here, and I'm missing a methyl group over here. There we go. Give me a thumbs up. Tiana, give me like 1,000. I'm kidding. But give me a thumbs up if you follow me on the allylic carbocation. Good. Thanks, Amelia. Awesome. Okay. So we've got these two allylic carbocations. Now what I'm going to do is I'm going to delete the curved arrow that I used to draw the resonance. So you saw that I just see that red arrow. I'm going to delete it. Okay. The reason I'm deleting it is because I'm going to use these carbocations to draw the nucleophilic attack. Okay. So now what's going to happen is that the chloride could attack this carbocation, or the chloride could attack this carbocation. So let's draw our chloride. There it is. Chizoink. There we go. Draw this one. Okay, so now we're going to draw nucleophilic attack here. And we're going to draw nucleophilic attack. Oh, oops. Where am I going? We're going to draw nucleophilic attack over here. All righty. So let's draw what we would get from that. So let's see here. We end up with a stereocenter in the first one, don't we? So we end up with a stereocenter that looks like this. So, right, this is a chiral center right here. And so this is going to be racemic. That's supposed to say racemic, if you can believe it or not. So racemic, son of a gun. Racemic. There we go. So there's one product. And then if we draw the product over here, this one we don't have a stereocenter. So we just end up with the chlorine over here. Okay, so that's one possibility. I just realized I'm going to need even more space than this to solve this thing. Okay, so these are the first two compounds that you could make. I'll put them in green boxes. I'll put this one in a green box. So here's one, here's two. All right, is everybody with me so far? So all we did is we made an allylic carbocation, we drew the two resonance forms, and then we did a nucleophilic attack. Okay, now since we have a conjugated system and it's asymmetrical, that means that I can do I can make a different allylic carbocation, can't I, right? That means I could add my proton here and have a positive charge here, and that would be another allylic carbocation. So we're going to switch over to a blank document, and we're going to draw that one as well. So just bear with me, and I'm going to go over to a blank document here. So is there any room on here? Boy, not a whole lot. All right, so let's see here. This is question 16.6, 16.6 B. So I'm going to redraw the starting material, which looks like this, something like that. Son of a gun. Looks something like that. There we go. I'm missing a methyl group here, aren't I? There we go. All right, so we have our HCl molecule. Right, and now we're going to make a different allylic carbocation, and so we're going to add the hydrogen here. So that's going to make a different allylic carbocation. Let's pencil it in here. It's going to look something like this. Oops, maybe I should have put my methyl group in first. Okay, we'll put the positive charge here. So there we go. And does that have a resonance form? Oh, you bet your Bobby socks it does. Absolutely it does. It's got a beautiful resonance form that you could draw like this. Maybe I can make a better arrow. There we go. We're going to end up with something that looks like this. There we go. And we have our positive charge over here. Audrey, you're always there. Audrey, can I have a nucleophilic attack on both of these allylic carbocations? Yes or no? Can the chloride attack? Yeah, absolutely. She says, yes, sir. Completely correct. Okay. So we're going to take the chloride. We're really going hog wild here with the old products. You're thinking you already had one that was racemic and then another one. That's three, and we're going to make more. So I'm going to delete that resonance arrow, and we'll just draw the nucleophilic attack here. So we'll get a racemic a mixture there, and here there's no chiral center. So let's draw that. So here we go. We end up with this guy. So that's racemic. So I'm going to scribble that down here. Racemic. And then we'll draw this guy, which doesn't have a chiral center in it. So it looks something like this. There we go. And the other two products. So what were the other two products, if I remember correctly? I can just kind of figure it out in my brain here. So one of them would have been this guy. We have the double bond here. And then the other one, so this one is racemic, of course. And then the other one would have been, if you do the resonance form, would have been this. So where we have the double bond here. There we go. So that would be the other one. So these are the ones that I had on the other page. And look at this. We have a total of 1, 2, 3, 4, 5, 6 different products that can be formed. Is it just me, Jerry, or is that a lot of products? You know, that's a lot of products, George. You know, that's a lot of products. That's my Seinfeld thing. All right, give me a thumbs up if you're like, I get it, but I will need to practice it. If you told me you could do this without practice, I would say you are like Goodwill Hunting or something. I mean, that would be crazy. Okay, if you could do that, that would be very difficult. So what I would like to do then is, hopefully everybody follows along with me. I'm hoping that, you know, I know you're all great students and you come to class with a piece of paper and a pencil, even though this is remote. And this is 16.6, and this is question C. So we have a conjugated diene, right? Double bond, single bond, double bond, okay? Then we have a geminal dimethyl at the top, which would make it symmetrical, but then they stick a methyl group over here to make it asymmetrical. And so we're going to treat this with HBr instead of HCl. And with this one, you would end up with a total of 1, 2, 3, 4. So you'd end up with a total of 4 racemic products. So 4 products, all racemic. Every single one of them is going to be racemic. I'm going to move this out of the way, and I'm going to get you started on one of them, right? So what's the criterion for the carbocation we're going to make? What kind of carbocation does it have to be? Anybody? I don't care if you spell it correctly. Doesn't matter. What's the criterion? We're not going by Markovnikov now. Exactly. Thanks, Maria. We want to make an allylic. Thanks, Jalen. We want to make an allylic carbocation. That's absolutely correct. Why don't we start on this side? Son of a gun, Mr. Dion. What are you doing? Let's get a pen here. There we go. Okay, so let's just do this. Put a proton there. And let's draw the carbocation that results. So here's our, son of a gun. Here's our positive charge. We have our gem dimethyl. Okay, then we can draw the resonance form of that. So we'll end up with something that looks like this, right? So we have the positive charge over here, and we have the gem dimethyl like so. All right, so can our nucleophile, our bromide ion, attack both of these? Oh, yeah, absolutely it can, right? So let's draw the bromide. Now I'm going to do my deleting of the resonance arrow again, or the resonance curved arrow, I should say. Okay, just so I don't have to redraw everything a million times. So we're going to have a nucleophilic attack here, and we're going to have a nucleophilic attack at this carbocation. So let's draw the products. This product is going to look a little something like this. So, oops, that's not very pretty. We have a double bond here. Got a bromine here. Now that's a stereocenter, isn't it? So this would be racemic. If you're wondering, why the heck do you keep saying racemic? Like, how do you know this? Well, remember that when you have an sp2 hybridized carbocation, it's trigonal planar. And so the bromide can attack from either face of the molecule with equal likelihood. And so we're going to end up with a racemic mixture, right? Just a little review from organic 1. And the same thing here, right? The bromine can attack from either face of the molecule. And so we end up with this here. And this would also be racemic. All right. So what I'd like to do now is take a short break, and I want to give you an opportunity to try and draw the other two racemic products. So here's two of them. They're both racemic. There are two more. So I'd like to give you just a short break. Try to do it, and we'll come back and we'll do it as a group. And then after that, we're going to talk about how you can control this reaction. So we'll get into a little bit about something called thermodynamic control and kinetic control. So see if you can draw the other possibility. So what I'm going to do is this. I'm going to copy this part here. So copy this, and I'm going to paste it down here. So paste, come on, paste. All right. And what I'm going to do is I'm going to delete the curved arrows, because at least delete that one. All right. You know what? Let's take a break, and I'll give you a chance to do it.